Jeff. Jeff is professor of linguistics at Stony Brook University, and he also has a joint appointment in the Institute of Advanced Computational Science at Stony Brook. He does research in several areas, including theoretical, computational, and mathematical linguistics, grammatical inference, computational learning theory, theoretical computer science, robotic planning and control, and artificial intelligence. Yeah, his PhD was from UCLA in 2007, and he was at the University of Delaware for a while before we were fortunate enough to entice him to join us at Stony Brook already a good amount of time ago. And it seems, how long, Jeff, have you been at Stony Brook?
Been 5 or 6 years, it looks like.
Yeah, and he hasn't.
It's gone by so fast.
Yeah, and he doesn't seem to regret it, at least as far as I can tell, which is, well, I will take that as a collective compliment to the collective. It has been a huge shot of adrenaline and excitement and just raised the level of the whole department to have Jeff with us, as those of you associated with Stony Brook know. So today the plan is that Jeff is going to talk to us about what's new in mathematical linguistics, and we'll do it in the format where if you want to put questions in the chat or raise your little electronic or real hand, it will be up to Jeff whether to take those questions as they go by. Usually that's just clarification, or put them off to the end for a fuller discussion. But with no further ado, I'm going to turn it over to Jeff Heinz. Thanks, Jeff.
Yeah, thank you very much for having me. It's great to be here. It's great to have so many people around the world, interested to hear something about mathematical linguistics. So thank you all for joining and spending the time today, wherever you are. I guess I do have, I guess I'll share my screen. I have some slides here that I can talk about, but I'm also happy to answer questions during the, as we go along. So if you have any questions at any time, like John had said, put them in the chat or raise your hand. I'm hoping that some of the other people, like either Shihan or Vinny, can monitor that for me, since I don't seem to be able to, I'm just not sure I'll be able to monitor it myself so well. So just let me try to get things up here. Okay. So yeah, so today I'm going to talk about, things that I think are new in mathematical linguistics. And I just want to, my thesis today that I'm trying to convince you of is that, mathematical linguistics is not a fossil from a former era. I mean, we all know it had its a golden era in the 50s and 60s and early 70s. But then it sort of, I think it sort of lost, in my mind, it sort of lost some focus in the 80s and 90s and maybe even the early 2000s from, mainstream linguistic theory. But I think it's always been there and it's always been really important. And so I want to, try to generate a little bit of excitement about what it contributes. And I think it continues, and it has over these, since the founding of Generative Linguistics Enterprise in the mid-20th century till now, mathematical linguistics continues to play an essential role in our understanding of natural languages. And it continues to make critical contributions to our understanding of how things which compute language, whether they're machines or humans, how they can learn the kinds of things that we have learned to do when we speak and process and understand natural languages. So this is sort of my main thesis that I want to talk about today. And I'm going to do it first by spending a little bit of time just talking about what mathematical linguistics is, because I think there's questions about that. And then I'm going to talk about the past, present, and the future. Okay, that's basically what the plan is. And I see a question about slides being available to download. Yes, they are. Should I put them in the?
Yeah, just stick them in the chat. Stick them in the chat. Put them in the chat. We'll post them on the website later.
Yeah, I'll put them in the chat right now.
Thanks.
If I can find the right file here. Okay, it's titled "What's New.pdf." Okay, so what is mathematical linguistics? Well, when I was a graduate student at UCLA, Marcus Kracht, who's a who's a mathematical linguist, he said, it's a way of thinking. And I think that's really important. More than I would say like a particular body of knowledge or anything like that, it's a way of approaching things. And, a key part of this is going to be abstraction, which I'll get to in a moment. Eugenia Cheng wrote this book recently called How to Bake Pie. She's a mathematician, I think, at Princeton or something like that. And she says, math, like recipes, has both ingredients and method. In math, the method is probably even more important than the ingredients. Okay, so, and she goes on to say that math is there to make things simpler by finding things that look the same if you ignore some small details. So this is what abstraction is. Abstraction is sort of ignoring certain details. And she goes on to say that abstraction can appear to take you further and further away from reality, but really you're getting closer and closer to the heart of the matter. I just fully agree with this. And I think there's a lot of work today, both in computer science and data science, in psychological sciences, that really wants to move in the other direction. They want to pay attention to all the details. They want to, they don't want to abstract away. But I think it's fundamentally the way we have to proceed. And I think it's sort of one of the methods, the key methods of mathematical thinking about anything, including language. Chomsky, in his book, The Minimalist Program, says something similar. He says, idealization, it should be noted, is a misleading term for the only reasonable way to approach a grasp of reality. So, Chomsky, in usual style, just going full on the, abstraction, he's just, and I think he's right. I think it's basically right. Maybe the word only is a little strong, but I think this is the right idea. Now, when you look at abstraction, there's always this question of, how abstract should you get? And this is a difficult question. So, there isn't just, it's not obvious what the right level of abstraction is. And so I think actually a lot of the work that we do is sort of trying to find, we explore different levels of abstraction, and we sort of see what we can get or not get out of it. And so I think there is a real question of what the right level is, but there's many different levels. I would point out that, even if we think the figure on the right with the red square and the black rectangle is sort of too abstract for the arrow in the heart, I would just point out that we should be careful of thinking that things are too abstract. In the history of mathematics, so many times concepts that we are comfortable with today were once considered to be too abstract. The number 0 was too abstract at some point. The real numbers, which are also called irrational numbers, are called irrational numbers because when they were first discovered by Pythagoras looking at the hypotenuse of a square, these were crazy numbers. They were irrational, okay? The square root of -1, those are called imaginary numbers. These things were really problematic when they were first posited. And now we sort of accept them and we use them and we don't, necessarily think twice about them. The same thing with number theory. That was just too abstract. Well, it turns out all of our electronic, bank transactions are all now made possible because of cryptography, which is based on number theory. So things that are too abstract, being too abstract to me is not necessarily a bad thing. And so I think we are often, anyway, maybe I'm talking to the wrong audience, but this is, I think abstraction is a fine thing, and I think that has a lot to do with mathematical thinking. What are the goals of a mathematical approach to thing? Well, I think a lot of it comes down to deducing consequences from premises. And so in some ways, language is a complicated, messy system. There's many different factors that are involved. And what we want to do is we want to abstract to some kind of clear statement of a problem, and then we want to solve that problem. And then we have to do this other thing where you want to then translate that solution back to reality. This is just the most basic way we do everything, and I think this is what the mathematical way of thinking is. And so, I'm not saying anything I think that's particularly controversial. I just think this is often maybe forgotten or overlooked. And I think it's what we do. I mean, some of the disadvantages of mathematical thinking is the abstraction and realization steps can take additional work and time. I'm very fond of making abstractions and getting problems and solving them. And I don't do as much work on the realization side, perhaps, as I should. So people have, said to me, well, it'd be great if all these algorithms and stuff you come up with, we had a software package that implemented them and blah, 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 blah. And they're right, it would be great. But I guess I'm just more attracted to this side than to this side. And I will just point out that there are other people who have gone ahead and built those kinds of tools for people to use, and that's been fantastic. So, everyone's going to have their own, place where they fit into this, but I think this is, there is a disadvantage here, which is that these steps, what's the right level of abstraction? How do you form the problem? And this step, these can be hard steps. But that's the idea. So the next part of this talk, I want to talk about the past. So what do we know from mathematical linguistics in, say, the 20th century? What did we learn from the 20th century? And one of my teachers at UCLA was actually Ed Keenan, who is a well-known mathematical linguist. He's now retired. Oh, and I guess what I should say is this entire talk is in some sense kind of personal. I'm not going to give really a comprehensive history of mathematical linguistics, nor am I going to give a comprehensive review of what's going on today in mathematical linguistics. So it's going to be kind of a personal selection. Okay, but I think it's still going to be, I'm hoping it's still going to be interesting for you. So there's a lot that I'm not going to go over. So for example, 19th century, the work by George Boole and Frege, very important and is informing stuff that I'm doing today. Bertrand Russell, Church, Turing, Post, the Polish logicians. I mean, there's so much work that was done that has led up to things that we're doing today. In the 20th century, you had people like Montague, Bach, Munich, Savage, Johnson. These guys have done fantastic work. And I don't really have much, I'm not gonna have much to be able to say about them. So I'm really focusing on specific contributions in the latter half of the 20th century, which directly contribute to my own interests, okay? And so another one of them is, so Keenan, getting back to Keenan, you might be familiar with the theory of generalized quantifiers. So I'm gonna talk a little bit about this because it really informed my own way of thinking about things. So the theory of generalized quantifiers addresses determiner expressions like every, all, some, more than 3, how many, fewer than 20, more male than female, less than half, and so on. And so you can put these kinds of determiner expressions into sentences like the one here, where you would put the expression where this line is, and you would say something like, some birds fly south for the winter, or more male than female birds fly south for the winter. And the question is what are the possible denotations of these expressions? This was a question that Keenan and Stavi were asking, 40 to 50 years ago. And a related concept is when you're asking what are the possible denotations of these expressions, what characterizes these expressions in natural languages is how arbitrary can they be, right? So is there a universal grammar that constrains the kinds of denotations that these expressions can have? And so this was what led them to this notion of conservativity, which I'll try to explain in a moment here. The basic idea of something like the word all birds fly south for the winter, is that its denotation can be expressed in this kind of way. All PQ would be true, provided that the P things are a subset of the Q things. And so in this statement, all birds fly south for the winter, the P things are the birds, and the Q things are the things that fly south, for the winter. So the idea is that the set of birds is going to be a subset of the things that fly south for the winter. And if that's true, then that would make sense. That's how you would make sense of the denotation of all. So that's the idea. And what Keenan and Stony proposed was that this notion of conservativity was that a denotation, so if you have some generalized quantifier, some determiner expression D, that it would be conservative if and only if whenever you had dpq, whenever that was true, it was also true for dpr, or if they're both false, whenever they equal themselves, that's only going to hold whenever the intersection of P and Q is the same as the intersection of P and R. Okay, now this is a little, it's hard to, if you haven't seen this before, this will be hard to sort of grok in this very short, presentation, but informally what it means is that when you want to decide whether all birds fly south for the winter, when you're evaluating, DPQ, you're ignoring the elements of Q which are not in P. Okay, all you really care about is the intersection of the elements of Q and P, or say the intersection of R and P. You don't care about elements of Q that are not in P. And that's actually, it's an abstract idea, but it's actually turns out to be very restrictive. And we can think of logically possible, and Keenan and Stony did, they thought of logically possible denotations of determinant expressions that are not conservative. And one of them is this one by, actually I think it was Hartig is the name of the person who thought of this one, is suppose you had this expression Hartig. And so you would say something like, Hartig birds fly south for the winter. Hartig birds fly south for the winter. And that would mean that the number of birds that fly south for the winter is the same as the number of things that fly south for the winter. I'm sorry, as the number of birds in the world are the same as the number of things that fly south for the winter. Okay, that's what it would mean, right? So that would be non-conservative because you have to care about even the Q elements that are not in P. Okay, so that would be, that's what this conservativity is. Then it turns out most logically possible denotations of these linear expressions don't have the property of conservativity. Okay, so this is a bit of a, so what does this mean? I mean, this is Ed Keenan from, 30 years ago, when this was the most, detailed image you could have on the internet at the time. But like, what it means that of all the logically possible ways you could decide whether, something P's or Q's, whatever that something expression is, only a small minority of them actually satisfy conservativity. And his claim was that all of these expressions, like the ones here, not just in English, but in any language, have this property of being conservative. And that would be a sort of principle of universal grammar that's going to hold true across all the languages. Now, there have been a couple of, this led to some literature where people said, well, what about the word only in English? And there was some, counterexamples here and then people have talked about. And, there may be some counterexamples. I mean, I think it's sort of an ongoing issue today, but it's certainly striking how many of natural language quantifiers actually fall into this space. And there might be just one or a few others that are sort of outside. So at least as a first approximation as to what, as to a characterization of the kinds of denotations generalized quantifiers can have in natural languages, this is pretty good. And this really impressed me because I always just thought, and Keenan would say, like, no mathematician would ever look at this question of conservativity. It's like, in and of itself, maybe it's not interesting. It's only because of the linguistic question that it becomes interesting, because it has something to say about, languages. And I thought that was really striking. And this is really sort of this kind of picture of, okay, what's logically possible out there when we think about phonological patterns or morphological patterns or syntactic patterns. We think about what's logically possible. How could languages be organized? And then when we look at how human languages actually are organized, are there sort of abstract properties like conservativity that seem to pick them out and put them in a very small corner of that logically possible space? To me, that sort of, that was very motivating. And that was a big lesson, I think, in mathematical linguistics from the 20th century that, I've carried with me. I'm sorry, I haven't looked at the chat for a while, so I don't know if there's questions there. But look, thankfully, there's no questions. So I'll just keep going. And if you want to learn more about this, Ed Keenan with Larry Moss, who's a mathematics professor at Indiana University, have written this great book that was published a few years ago called Mathematical Structures in Language. It talks about conservativity. It talks about many other things, and categorical grammars and the syntax and semantics and things like that. It's a great book, and I highly recommend it. Okay, so the rest of this talk is going to be looking at now the mathematics of sequences. And so, why would we care about the mathematics of sequences? Well, languages unfold over time. So we're observing, and when we observe an utterance or anything like that, it's a sequence of linguistic events. And so we might think about what the mathematics of sequences is. And in linguistics, we also care about other kinds of structures like tree structures and maybe graph-like structures. So we can also think about the mathematics of these other kinds of structures as well. And we will, when we get later on in the talk. Oh, I see someone raised their hand. Go ahead.
Yeah, Jeff, I just wanted to read a question in chat by Adam. He asks that could conservativity follow out for the fact that D has to take NP and modify, and no NP would denote the set of everything?
Yeah, so it's a good question, and so I don't. In some sense, the determiner is.
I can try to explain what I said because typing up is kind of silly, and for me.
Yeah, go ahead.
So what I'm trying to say is that if we assume that the quantifiers are really in the determiner position, and can we deduce from syntax that if a quantifier is in the determinant position, it's a modifier of some NP, right? And the NP will denote a set of things, but will not be set of everything that is out there, right? So that's why you have every book, some book, and so on. And book is obviously a subset of everything. And hence, that's what conservativity comes out from, just the sheer fact that a quantifier modifier is always an NP. The only exception will be, I guess, if some people believe in sort of a derivational way of doing everything, that, every plus thing, if the denotation of thing, meaning every, all the stuff in the world, that would be non-conservative. But otherwise, it's kind of conservativity seems to be, for me anyway, and I wonder if that's true, because it would be interesting, falls out from the fact that there's modification.
It may do that, and I think it'd be interesting to pursue that line. I don't know if anyone has pursued it. And so not because I'm an expert on the conservativity, it's because I'm mostly work in phonology and morphology. So I would take a look at the literature on conservativity since Keenan and the Stony paper and see what people have said. I think the thing to realize is that, in something like all birds fly south for the winter, there are two arguments that are necessary in order to evaluate what the truth of the statement. So you've got to have both P and Q. And I guess what you would be trying to claim is that the syntax is such that you don't really need all of Q. What you need is something like Q minus P, right? And that would be, so that's the part you'd have to explain. Why does the syntax say that you don't need, all of Q, you just need Q minus P? And so I'm not sure how that step would happen, but I think that's the step that would have to happen. Again, you want to think about it like what in the syntax would prevent you from having a quantifier that would allow you to, or a determiner expression that would say something like this, where you say like, all birds are green. where, I'm sorry, heart-take birds are green, which would be true if the number of birds in the world was the same as the number of green things in the world. Like if you sort of force yourself to do this, you can kind of make sense of that, but it's a struggle. I think it's a great idea, and I think it's worth looking into. I don't know the answer, but I also think that in the syntax semantics interface, I think this is where actually a lot of exciting work can happen, because you can, and if you look at the categorical grammar literature, that's what they do, is they have syntactic operations, and those syntactic operations have sort of clear semantic counterparts. And I think that's, that kind of compositionality is exactly what we want. We want to sort of identify the nature of that. So you could very well be right. I just don't know. Okay, was there anything else there? And okay, so coming back to the sequences, let's talk about sequences for a moment. Knowledge of language includes knowledge of which sequences are licit and which are not. This, of course, is a lot more to language than this. We just talked about, the meaning of sentences and things like that. But certainly we should be able to distinguish between a sentence like John laughed and laughed in English versus a sentence like John and laughed. Okay, so we can ask questions about this. And this brings us to what's called formal language theory. And in formal language theory, we're interested in this problem called the membership problem. So the idea is you have a logically possible set of strings, and then you've picked some set of strings. This is, or some, when I use the word string, again, I just mean a sequence of symbols. So I'll use the word string and sequence of symbols just interchangeably. I might have some set of sequences here, some set of strings out of all the logically possible ones. And I want to have some kind of device, some kind of machine, or some kind of, that will take a string and tell me, yes, it's in the set S, or it'll take the string and say, no, it's outside of S. In the same way that in this example, English speakers will, given a string like John laughed and laughed, will say, yes, that's grammatical, but John and laughed, no, that's not grammatical. Okay, so what is this machine M for these kinds of, for some strings, sets of strings like this? And so and this, by the way, there's lots of variations on this. I mean, so sigma star is the notation we use for the set of logically possible strings, all possible strings of finite length. That's sigma star. We might consider like membership problem where we're getting true or false. It's in the set or it's out of the set. We can imagine transformation problems. Actually, I think a lot of linguistic generalizations, whether they're phonological processes or morphological processes, we can think of taking a string and getting back another string. So, if you're doing affixation, if you're doing vowel harmony, all these kinds of processes are transformations over strings. There's lots of variations on this, but these are all functions on sequences. They're all functions on sequences. Some people like to do probabilities and things like that. We can look at that kind of stuff. Okay, and I will point out that mathematics, tends to classify numerical functions according to all kinds of properties, whether they're linear functions or polynomial functions, trigonometric functions, logarithmic functions. I mean, we actually have a very rich vocabulary in mathematics because there's been thousands of years of study of numerical functions. So we can talk about continuous functions, we integrate, we take the derivation, we find the derivative, we do all these things with numerical functions. But how much do we know about functions over sequences? When we look at sequential functions, do we have the same vocabulary? And we don't. And the reason we don't is because this field of study is about 100 years old or less. And I will talk more about some of this stuff later, but part of what we're doing today in the 21st century, I think, is we actually have a much better understanding of these kinds of, we have a much richer vocabulary now of sequential functions. So the basic question is, how do we classify functions like these above? In the 20th century, we had our first sort of classification. And this is an image from a Nature article from 20 years ago by Noack and Partheni Yogi and Komarova and others. And I think this is a really great paper to look at. It's about learning theory, actually. But this is a nice image because he shows you sort of the main you had a basic phrase structure type of grammar. You have what's called the context-sensitive grammars, the context-free grammars, and these finite state grammars. And they're nested. So everything that's finite state is also context-free. Everything that's context-free is context-sensitive. And this gave us kind of a coarse-grained way of thinking about these membership problems, these formal languages here that we could think of, these sets of sequences. We can ask, where do they, can we describe it with a finite state grammar? Yes or no? And if not, then we see, can we do it with a context-free grammar or context-sensitive grammar? Okay. And so this is, this is a coarse-grained understanding that we have. This Nature paper is really about learning theory, and I'll just point it out because I care a lot about learning theory, though I don't actually have much to say about it in this talk, is that the crucial result of learning theory is that there's no procedure that could learn an unrestricted set of languages, and so that's why there has to be this sort of restricted set. And so this is the, in this paper they put forward this idea that universal grammar is really some restricted set in this space, and that's going to be a learnable class. But okay, so we can ask this question like, where is natural language? Okay, so this is similar to what Keenan was asking before when he looked at all these generalized quantifiers. He was asking, what kinds of quantifiers are these? Well, if you put natural language patterns into this sort of space, and here we have the context-sensitive region, we have the context-free region. This regular region here is what was called the finite state region in the other one. So this term regular, as we'll see, is going to means finite state. Okay, and what we'll see is when you put patterns in here, if you look at like the kinds of consonant clusters we allow in English, you can describe those with the finite state machine. If you look at the long distance sibilant harmony pattern in Chumash, you can describe that with the finite state machine. Quacutal stress is this known as this sort of default to opposite stress pattern. That's also, you can do that. But what Chomsky pointed out, at the beginning of his career, was that English and other natural languages, because of these nested embedding type patterns, you can't do them with these so-called finite state type devices. With these regular grammars, you need something more powerful like a context-free grammar. And later, Stuart Schieber and actually Hubrex argued quite well that you actually need to go beyond context-free into the context-sensitive region. And then there's been a lot of discussion by Aravind Joshi and others about how far out you have to go into the context-sensitive region, and it's a very interesting question. But I guess my point is that what we want to do is, like, this is not the end of the discussion. It's actually the beginning of the discussion, because what we're interested in is something like this. This is sort of the idea of, okay, well, what's the subclass that's going to get us all the natural language patterns, but not the stuff that we don't see? Like, what's going to characterize is natural language arbitrary? Could any pattern in this space be a possible language pattern? I would say no. There's a lot of crazy stuff in this space. So we want to try to find something like that, or maybe even something like this, where the idea is that, the phonological generalizations will belong into particular spaces here, and maybe syntactic generalizations will also sort of scatter across the space. But the idea is to try to find, natural classes or natural subclasses of these regions that are actually, meaningful and describe something about linguistic, the nature of linguistic generalizations. So that's sort of, like, that was the past. I mean, and again, I skipped a lot of other stuff, so it's not comprehensive in any way, but I think you can sort of see why, I'm going to, get to what I'm getting to, which is the present. Like, what have we done now in the 21st century? What are some advances that we've made in the past, say, 20 years? I think the main advances that we've made is the granularity of our characterizations. As I mentioned, these regions of, regular, context-free, context-sensitive, those are very coarse-grained characterizations. And we now have we have a much more fine-grained understanding of these things. And I'll show you some examples in a moment. Especially with sets of sequences, formal languages, and these transformations over strings, we have a much better sense of the much more fine-grained understanding. And so we can actually begin to locate much more precise characterizations of where natural languages patterns actually fall. Something that I'm not talking about so much in this talk is we've also been able to connect some of these characterizations to computational learning theory. So we're able to say, not only do natural languages fall into this small class, but that small class is learnable. Like it has properties that make, when you're given data, just positive evidence, you're able to generalize successfully to sort of a target pattern. I'm not saying all the answers are solved, though there's still a lot to do. We have to connect it more to acquisition and so on. But there's progress there. And I think one of the most interesting things that I have to mention, because it's, a lot of it's happening here at Stony Brook University with Thomas Graf and other colleagues, is sort of this interesting way of trying to unify some of the computational analysis of syntax, phonology, and morphology via representation. And this is the important part of where the tree structures come in and things like that. So I'm going to talk about these three things. And I realize now that I can't remember how much time exactly we have. But again, just feel free to stop me, John, when you want.
No. Here, let me just, instead, I would not stop you, but I will update you so that you can think for the next section. So we really have until 2:20 total time, including questions and everything else. Okay. Because there's another event at 2:30. So 2:20 is the cutoff. So it would be great if there's still 15 minutes for, discussion and questions. So that leaves you about 20 minutes.
Okay, that's fantastic. So, as I mentioned, the distinctions we had before between, say, general phrase structure, what we now call computably enumerable patterns, context-sensitive patterns, context-free patterns. These are very coarse-grained distinctions, but we have finer-grained ones. So, for example, if you take a look at this regular space, just look at the regular space itself, we can break it apart into these other classes. Okay, and I'm going to talk a little bit about these other classes now, but not in so much detail. And the other, the forward reference here is that, these subregular classes, when you apply them to tree structures, they actually let us probe some of these non-regular string sets that are up here, which I think is actually, something I'll get to. I have a slide on it later, but the idea is that, again, these things right here are all about sequences, and we know linguistics is more, it's not just about sequences. I mean, sure, events unfold in time, but there's a more abstract structure going on with these dominance relations and so on that are encoded by by trees and other kinds of tree-like objects. And so, although I'm going to be talking about, and I'll give you examples from phonology and morphology, the mathematical ideas that are here can be extended to trees, which amazingly will let us probe what's going on up in this area. Okay, so that's one of the things that is new in the 21st century. So, I'm going to talk a little about regular computations. So regular computations, we can think about them in at least three ways. People who've done some, programming before may be familiar with the regular expressions. So, this regular expression here, A star, will match any sequence that has one or more A's, in contiguity. So, this is a finite state acceptor. It's where that term finite state comes from. You've got finitely many states, or these are these nodes in this graph, the vertices in this graph. And then you have to see 1A, you're going to start in state 0. That's what this arrow means. This is what's called the accepting state. You read the A, and then you can stop or you can loop. So you could generate, you can generate sequences here of at least 1A or of 2 A's, of 3 A's, 4 A's, and so on. So these represent formal languages. These are sets of strings that consist of one or more A's. And here's a logical formula. Depending on how familiar you are with logic, will be, although it looks like a bunch of symbols, it's hard to read. Logic actually becomes easier to read with practice, like any foreign language actually. And this basically says for all X. So here these variables X are referring to like positions in your sequence. So it's like for all positions in my sequence, X has got to be an A. Okay, so I'm only looking at sequences of A's, and there has to be a position that's an A. So I've got to have at least one A in my sequence. That's it. So these are three different ways there's sort of three different grammars for talking about the same kind of sequence. Okay, and we can so anything that you can, any kind of logical formula, actually it would be monadic second order logic. This is the first order logic, but monadic second order logic is more powerful, but that would be any kind of MSO sentence, a regular expression or finite state acceptor would give us a regular computation over sequences. Here's a more linguistically, motivated example. So in Morangaku, there they have a stress pattern where the first syllable is always carries the primary stress, and then stress falls on alternating syllables. Okay, as you can see in these other in words that are as they get longer and longer, and they just perfectly alternate. That's how the stress pattern goes. So how could we describe this with logic? Well, this slide is showing you how you describe it with logic. The basic idea is that an expression, a well-formed sequence of syllables in this language would have to satisfy these 4 different constraints. They'd have to satisfy the constraint that they can't have a clash, they can't have a lapse. So a clash would be 2 stressed syllables together. A lapse would be 2 unstressed syllables adjacent to each other. And then they have to start with a primary stressed syllable. That's what this little anchor symbol here is indicating the left edge of the word. So you have to start with a primary stress syllable, and you can't have a primary stress anywhere else in the word. So these expressions are defined up here. So for example, we can say, what's a clash? A clash is when you have 2 positions, X and Y, and they're next to each other. So this funny triangle just means the positions are adjacent to each other. And X is stressed and Y is stressed. Well, what does stressed mean? Well, stress just means you have primary stress or you have a secondary stress, for example. Okay. So this is saying, you have a clash when you have 2 positions that are next to each other. And in Morangaku, we're requiring that you don't have a clash. So you have the negation there. Okay. Lapse is where the 2 syllables are unstressed. And to get the primary stress, we have to use a first. Anyway, so you can look at this and take it apart, but the idea is that you get a nice sort of explanation here or you get a nice logical description. This looks kind of long. We had to write many lines for it, but it's just because it's I think the logic actually, when you get more complex examples, the logic actually simplifies things compared to regular expressions in the finite state acceptors. But we could also describe, the stress pattern in Morangaku with regular expressions or with finite state acceptors, and they would look like this. And so here in the finite state acceptor, we start with the primary stress, then you see an unstressed, and then you see a secondary stress, and you just loop around, and you can end in either of these states. So that's a very simple machine. When you get more complex machines that require many more states, they become much harder to understand. And that's in contrast to the logic, which is always sort of much more purely compositional and easier to follow. Here, this regular expression is basically saying, yeah, you've got to start with the primary stress, and then you can have 0 or more. This is what's called the Kleene star, 0 or more of these guys. But that's only going to give you words with an odd number of syllables. So that's why you also have to have, plus, so in addition to, you start with this guy, and then you have, 0 more of these, but then you can end also with the unstressed syllable. So these are just different ways of describing this stress pattern. Okay, and it's a regular computation. And right now you're thinking, okay, well, so what? So we can do that. What's the big deal? I mean, there isn't a big deal other than the fact that, the regular class of languages, as I mentioned, is actually a very, it's a very coarse-grained characterization of something. And actually, we have a much more fine-grained characterization, which we can organize. Here, I'm showing the organization by logic. So again, we're not going to understand this whole figure. It's okay. I just want to try to point out the main things here. If you have monadic second-order logic and you have what's called the successor relation, then you get this regular class of languages, which includes everything here. Okay, that's everything. If you only have first-order logic and you have this sort of successor relation, you get the smaller class, which is known as the locally threshold testable class. And then and that properly contains this class and so on. So there are all these subclasses here. And so we could ask, like when we look at patterns like Morangaku, you know, and when we look at other patterns, you know, phonotactic patterns and so on or morphotactics, you know, where do they fall in these regions? Okay. And what we find is, and again, the idea here is that the higher in the diagram you go, the more complex the logic is. The lower down you go, the simpler the logic is. Down here, we have the conjunctions of negative literals or disjunctions of positive literals. So, you know, this is just fancy logic talk that means here you say things like, don't have this kind of structure, and don't have this kind of structure, and don't have this kind of structure. And here you're saying things like, you know, in the disjunctions of positive literals, you're saying have this kind of structure or have this kind of structure. Well, it turns out that when we look at phonotactics in human languages, and we look at stress patterns like Mangaku, they're almost all at the bottom of this kind of more fine-grained structure. They're all either what we call SL, with strictly local, or the complements thereof, or this tier-based strictly local, or complements thereof, or, you know, so where are these? These are all these guys down here. They're the ones at the bottom. In other words, these are all logically possible patterns that could inform how stress works in human language, that could inform how phonotactics works, but they're never used. So there's something going on down here that's about how language works, about how phonotactics works. And so we're getting a much more precise characterization than people had in the past. And, you know, yeah, okay. So consequently, the patterns here are describable with simple logical languages and very well-behaved automata. And they're also, we know them to be local in particular precise ways, which I won't have time to go into so much unless you have questions about it. And they're also structured in a way that allows you to learn them with the right, you know, with the right kind of parameterization. So, you know, that's kind of a striking result. If we look at string-to-string transformations, we have a similar kind of thing happening. So the established foundational view, when you think about morphological patterns, whether it's prefixation, circumfixation, suffixation, infixation, truncation, the root and pattern morphology that we see in the Semitic languages, partial reduplication, or the phonological processes, whether it's local assimilation or dissimilation, harmony, epenthesis, deletion, all of these kinds of things that we see that change these sequences that make up words and phrases into other words and phrases. We had a very coarse-grained, it's absolutely correct, so I'm not being critical of Rourke and Sproat here at all. They're absolutely correct. These are all what we would call rational relations. And the only thing that was kind of funny was total reduplication, which seemed like an outlier because it was not a rational relation. And to describe this another way, you know, what this one NFT means, this is what we would call a one-way, non-deterministic, finite state transducer. So all of these patterns here that are rational relations, you can write a one-way, non-deterministic, finite state transducer. So I know that sounds like a lot of jargon, it is jargon, but what it just means that there's a grammar, a device you can make that sort of properly, you know, it's a well-behaved mathematical thing, and you can describe all these patterns with it. But you cannot describe total reduplication with it. Total reduplication is sort of outside the scope of these one-way non-deterministic finite state transducers. Everything else is in here. Okay, this was the view at the end of the 20th century. But now we have a much better understanding of this. Now we know that actually, in addition to these one-way non-deterministic finite state transducers, we can also look at what are called two-way non-deterministic finite state transducers. And total reduplication actually is easy to describe with this other kind of machine, okay? And by the way, the nesting here goes top down. So you know, these regular relations contain these guys, but it also goes right to left. So this guy also contains, you know, these guys. But the other thing is we also have, in the same way we could sort of dig into the regular patterns to look at these subregular classes like strictly local or whatever, we can also dig into these rational relations and look at rational functions or sequential functions even strictly local functions. So this local functions are the ones where how you decide what to, how you change the string just depends on sort of a local window of information. And it turns out that, this sort of unvariegated set of patterns here that people just said, well, oh yeah, we can write a one-way non-deterministic finite state transducer for those. They're just a rational relation. It turns out most of them are much more than that. They're actually these very simple kinds of local sequential functions. And total reduplication, while it's not one of those, turns out to be what we call, it's just literally the concatenation. That C just means concatenation of strictly local functions. And you can describe it with what's called a two-way transducer. So we just have a much better understanding of what's going on with these processes now. And this doesn't look so, unmanageable computationally as it may have before. Actually, it's sort of similar in a way to a lot of the common stuff that we see. It's not the same. There is a difference, but it's not, doesn't seem as wildly different as it may have before. So we're actually, these are advances. I've talked mostly about morphology and phonology, so I did want to say a little bit about syntax before coming to the end here. I'm getting to the end. And so, tree structures are a foundation to distinct theories of syntax. So Ed Stabler has this sort of review paper from 2019, which sort of goes through a number of different approaches to syntax. But he points out that like the tree structure is sort of central to all of them. This is sort of a very simple example here, sort of illustrating the notion of nested embedding that we have in English and many other languages do too, which is giving you this kind of, recursive structure that you cannot describe with a finite state machine. You can use logic and finite state automaton to describe tree structures. So they're not just for sequences. I mean, I spent a lot of time about sequences and about logic and about automata, finite state machines, but they're not just for sequences. People have devised and have studied for decades. I mean, the computational literature on tree transducers and tree acceptors, finite state tree acceptors, was really, it's over 50 years old. It, was the main scholars of that area are coming out of Europe. They're just, done phenomenal work on this stuff. And this is I can't explain this diagram in this talk, but this is just what the tree transducer would look like for this, these tree structures, this tree language here. It would be a very simple machine. Okay. Going back to these mildly context-sensitive string sets, so these more complex, string languages. What we have now, and this was sort of a realization at the beginning of the 21st century, not by me or my colleagues, but by people I know, like partially Ed Stabler, partially Thomas Graf, partially Greg Kobola, who were able to show that if you take a set of trees recognized by a finite state tree acceptor, so this would be a tree language, not a set of strings, but a set of trees. Let's call that T. Oops. And then you transform it with what's called a finite state tree transducer. So this would take the trees and change them around in certain ways. You get another set of trees. And then if you spell out those trees to yield the sequences they describe, you're actually getting, you can get the nested embedding and you can get the Swiss German type examples with the crossing dependencies. I don't know if you can do Yoruba copying, but we could ask Greg and find out. But this is kind of an amazing result because it says, here in this space, we can use the finite state machines over sequences and the logic that describes sequences to give linguistic generalizations. To get the string sequences in this space, you can use the finite state machines and the logic over tree structures. And then when you spell them out, you're going to get the stuff up here. And so that allows for this really interesting, I think where we are today is we have the following situation. So this is, again, sort of a historical recap of where things were. In the 20th century, we would say, okay, before we knew that syntax was sort of non-regular, context-free and above, it had, at least it had that power, but it looked like regular was sort of, an upper bound on what we needed for almost all morphology and phonology. Okay, maybe except for total reduplication or something. But now, and again, this is an overview paper. This is not all my work. I mean, this is people I've collaborated with and others. We've shown that phonology is actually, in a sense, properly subregular. We've got better characterizations and more fine-grained characterization. So it's conjunctive negative literals, or more generally, we might call it a quantifier-free logic. And we've also realized in the 20th century that syntax is actually regular, not over strings, but over trees. So the move that we're making is saying, look, over strings, it looks like, we have these context, sensitive pattern. They're over strings. That's what they are. They're context sensitive. Okay. But if you look at them over trees, they're actually, we can describe them this way. And what Thomas Graff and his colleagues are working on, our students here at Stony Brook are working on, is actually showing how the kinds of generalizations we need over for linguistic generalizations over these tree structures, we don't need the full power of the regular class. We actually can get away with something that seems like very similar to what we use in the phonology world. So there's this interesting unification where we can say logically or computationally the power is the same, it's just the representations are different. Now, if you keep the representations the same, then you're going to have this really strong difference in the computational power. So anyways, that's, I think, quite those are some of the, I think, advances that have come out in the 21st century. Okay, so the future is really just me concluding. So let me do that. I think mathematical characterizations of linguistic structure teach us that many, if not all, linguistic generalizations are subregular in some way, whether they're over strings or whether they're over trees. And that means, for example, that they can be described with first order logic, or actually even weaker logics, like a quantifier-free style logic. And I think these characterizations, and I haven't been able to talk about this much today, so that's just how it goes. But I think they do provide insight into locality conditions in linguistics, and also and other conditions on linguistic structures. And they help us understand something about language learnability, which again I wasn't able to talk about much. But the idea is that if you have if the notions of locality are sort of built into your universal grammar, as you hear data, you apply those principles, and then you're going to generalize. You're going to make inferences that you wouldn't otherwise make if you were sort of willing to consider all kinds of possibilities. I think in the future, we're going to continue to study, other linguistic representations. So not everything in linguistics is always strings and trees. We have autosegmental patterns in phonology. There's prosodic patterns, which are tree-like. And there's, we can look at features. So it's not always just symbols. There's properties that are shared among symbols that we want to look at in all domains of linguistics. We want to continue to connect these characterizations to both learnability and acquisition. So one of the things I'm excited about at Stony Brook University is we've got Jordan Codner, who does computational modeling of acquisition, cares very much about the kinds of data that children are actually exposed to, and to see if we can actually, generalize, sophisticated linguistic generalizations based on the kind of the sparse data that kids actually get. It's very different from what happens in, NLP world with Chat GPT and things like that, where they're actually, training these massive language models on, terabytes and terabytes and terabytes of language data, way more than what children get. People have calculated that, those massive language models that they use that we all use on our phones and everything, those things have the equivalent of 10 million people's lives of linguistic experience in their training. Well, kids only have a few years of life, and by which time they've mastered a lot of the sophisticated linguistic generalizations that we have in their native language. So, we want to know how to do that, right? I think we can continue to draw some more explicit parallels between disparate modules. So, for example, like WH movement in syntax and consonant harmony phonology. I've only looked at this a little bit, but they actually, when you look at it from the logical or from the computational perspective, these mathematical grammars, the grammars are actually very similar. Just one is operating over trees and one is kind of operating over strings. And so you've got this interesting parallel between syntax and a phonology in these processes that are these long distance processes, but they're happening in kind of different representations. And I do think it's important to develop applications and to scale them up, because we do want to be able to, people, a lot of this stuff I think does, the more applications you have and tools you can build and people can use, the more people will sort of, buy into it. So I think we have some catching up to do there, but I hope that happens also as part of this century. So thank you, everybody. That's the end of my talk. I won't take any questions you may have. I think we still have time for questions. I think we've got
we do indeed
questions.
We do. Thank you, Jeff, so much. And we recommend that people come back with cameras so we can have our discussion and we can see each other, and come back if you like into gallery view, and unshare the slides so we can all see each other. And if we need to put them back on, we put them back on. And it is open for the next up to 13 minutes for comments or questions or other kinds of speeches. So Alexander has a question in the chat, and Tobias has a question in the artificial hand raising category. So let's go with Alexander's in the chat first, and then Tobias. Is that okay? Alexander, do you want to read your question out, and Jeff, you can take it from here, of course.
Okay.
Yeah.
So basically my question is, what makes total reduplication so irregular? I just did not get it during the lecture.
Yeah, I mean, I didn't explain why, so it's not a surprise that you didn't get it. I didn't actually go through the reason why. But the reason why is not what we can do with a one-way non-deterministic machine is because there's no upper bound on the lengths of words. And so, the way if you have a machine that's reading a string, one left to right, one symbol at a time, you've got a word like pabalu, and you want to reduplicate pabalu. Now you want the machine not only to reduplicate pabalu, but other words, maybe a word like, ma pabalu, okay, and even longer words. So what do you have to do? Well, you when you read the P, maybe you want to write the P, but you have to remember that you saw a P. And so you can move to another state that says, okay, I remember I saw a P. Then I read the A, I move to a state that's got to say, okay, not only do I remember an A, I remember I saw a P before. So the thing is that you end up needing infinitely many states, and you can't do it with a finite state device, okay? So that's sort of the fundamental problem in generating a total reduplication with a one-way finite state machine. Now, the two-way finite state machines are actually, they allow you to go back and forth on the input string. So you basically can read it and write it once without memorizing anything. You go back to the beginning because that's what you're allowed to do, and then you can read it and write it again. Okay, and so generating is actually easy to do if you have the right kind of grammar. The two-way finite state machines were developed again 50, 60 years ago, but for some reason they never seemed to get the attention of computational linguists until my former student Josep Delatin and I sort of came across them, and we were just like, how come nobody has even looked at this? And so we have this paper in 2020 where we sort of go through this in more detail, which you can look at, but it explains, the issues and so on. But it was striking to us that, like, it just seemed to us, I think it just wasn't noticed. Like, I think there was a point when, the mathematical linguists and the computer scientists and the linguists were sort of all talking to each other, maybe in the 60s. And then somewhere it stopped in the latter half of the 20th century. And, I think we're trying to get people talking again, because there's been a lot of interesting work in related disciplines that can make contributions. By the way, I'm not claiming that when humans are, producing reduplicated words, that they're actually, following the sort of processing model of going one way and going back and so on. There's other kinds of grammars that you can think about that can compute the same functions. The two-way finite state machine is just one particular device that's able to do total duplication. Yeah, I don't know if that answer is clear, but that's the that's the idea. Tobias?
Yeah, thank you for the talk. I just want to make sure or try to understand whether I understood correctly your last bit, like the conclusion, like the 21st century thing. So do I understand correctly that syntax is demoted to the level of computational complexity of phonology because it has trees and because you operate your computation on trees, as opposed to phonology, where you operate your computation over strings? So if I understood, if that's the case, then it seems like there is a double complementary distribution between syntax and phonology. So phonology has linearity and syntax doesn't. So because a string means there is a linear order and trees means there is no linear order. Number one, and number two is that there is a dominance is expressed in terms of trees in syntax, but isn't in phonology. So there are no trees in phonology, because if there were trees in phonology, right, they would exactly coincide. Is my understanding correct?
Yeah, I mean, I think in terms of a general outline, I would say that is correct. That's the general outline that I'm giving. I do have some particulars I want to poke at, and I'm sure it will lead to. I mean, as you well know, there are people who have proposed dominant structures in phonology, and for good reasons. And they're, at the same time, I would say, so there's more to talk about for sure. But on the whole, I would say yes. The idea is that phonology mostly, I would say, deals with sequences, and that syntax mostly deals with trees. And if we make those sort of the base kinds of structures in each of these domains, then we can, in fact, use the same kinds of computational devices, specifically anything that's equivalent to, what you can do with a finite state machine or a particular kind of logic, like monadic second order logic, or it's probably something even much weaker. I would take issue with the claim that syntax doesn't have linear order. I would say that the tree structures that, as far as I know, most people look at, they do have linear order. They just also have dominance. So, for example, in the when you have the children of a node, if there's more than one child there, then those nodes are going to be in some kind of order.
Really? Well, Chomsky and minimalism says they are not. Linear order is occurring at linearization after syntax.
Yeah, I mean, I know that's what Chomsky says. I respect Chomsky a lot, but I just don't fully agree. I mean, I will say that with respect to the mathematical side of it is people do study, trees without linear order in the children and with linear order in the children. I know Chomsky will limit the number of merge only takes 2 items. I know in people want to have binary branching trees and so on. I'm not sure how much. So there are definitely proposals that don't that will say that you don't have linear order at all. I mean, that's true. That is true.
I just wanted to mention, you make me a happy person tonight to see that, but if I'm correct on my generalizations, because I'm working in a theory that says for 20 years that there are no trees in phonology. So.
Well, yeah, I would say, people have proposed, like prosodic structures, syllable structures that are tree-like in.
Oh, yeah.
What, I'm sorry?
Yeah, sure, of course.
Yeah, and I would say that there are reasons why we might want to have those kinds of structures, but I think when you get down to it, though, I mean, there's a sense in which what's happening is still fundamentally sequential in nature, right? So the syllables come one after the other. They're not. You don't get these same kind of complex tree structures. I know people have proposed, like Harry Vanderhulst, that you have, syllables can be recursive and things like that. So for everything that I'm saying, there are linguists who have argued against it. I mean, I don't deny that at all.
Oh yeah.
But I do think that the basic picture that I'm trying to put forward, that I think is exciting and we're thinking more about, is that from this computational perspective, it seems like phonology and morphology. I mean, morphology is actually the interesting hybrid. I would say phonology is mostly sequential, and syntax is mostly, tree structure. That means a dominance relation. That's fine. You've got to have the dominance relation to get the tree structures. There's no question about that. Linear order there, it's not as important in some sense, because it's the tree structure that's the crucial thing, which you get from dominance. But once you have those basic data types, then the computational mechanisms are kind of the same. And I think that's really interesting. And that's not a perspective I had even when I got my PhD. It was something I've only learned in the past like 10 years, and it's been pretty exciting. So if that goes along with what your own theory is proposing, that's great. That's a point of convergence. Okay, there was no other questions here, both in the chat, which I haven't caught up to yet, and then I see Adam has his hand raised. So I don't know if anyone's paying attention, we can follow the order that's most respectful to the.
Well, I think Daniel asked his question first in the chat. I don't know if he wants to elaborate on that.
Yeah. Okay. Great question. So this is a good question. I mean, what are the implications of some of the same processes applying different representations with modularity? Did you want to say any more about this, or should I can just right now, but if you want to elaborate, I'm happy to listen to you first and then go. Okay, so I'll just go ahead. I mean, I think the question of modularity is a good one. I mean, when I've spoken to other linguists, they've said, well, if I can do something like this in syntax, why shouldn't I be able to do it in phonology? Or if I can do something in phonology, why can't I also be able to do it in syntax? Like, why are things organized in a modular way? And I don't have an answer to that other than the fact that that kind of modularity is the norm and not the exception. Okay, so we don't have, and Randy Gallistel is a cognitive scientist, and so he has this book on like I think it's called Computational, the Computational Mind or something, but he has these great points. When you look at biological systems, and we are a biological system, specialization and modularization is the norm. We don't have a single organ that does all the things all of our organs do. Our heart pumps the blood, the liver cleans the blood, or the kidneys clean the blood. We don't have a general organ that senses. We have eyes that see, we have ears that hear, we have a nose for smelling, and our eyes are specialized. They can't see infrared light. They can only handle, visible light. Our ears can't hear any frequencies of sound. They're limited. Why are they limited that way? Dogs can hear much higher frequencies than we can hear. How come our ears aren't like dog ears? They're mammals too. So there are these sort of, strange constraints that may exist for some modules, but not for others. And, why that's the way it is hard, it's hard to say. But I don't think we should think of it as something that's unusual. I actually think it's the way things normally are. So yeah, I mean, I think there is something in our genetic endowment that says, yeah, phonology is going to be in this sort of basic, the phonotactic patterns are going to be in these sort of very simple regions in this regular class of sets of strings. And maybe syntax is going to be somewhere similar for simple classes of tree languages or something like that. We can then begin, once we have a better understanding what those characterizations are, we can begin to understand them. From my own view, I would say that learnability has something to do with it. We know that those simpler regions can actually be learned, whereas some of the higher regions, things get too complex, there's too many possibilities. Maybe you can do learning, but it's just going to take a lot longer. So there's something, but it's hard, so that's that. Okay, so then Adam had a question, which his hand is down now, but also then there's a question by Patricia in the chat.
Yeah, so just kind of a minor point in response to the previous discussion. So, I mean, there are parts of the phonology, in my understanding, I'm not a phonologist, where we do not see linearity like inherent. So, for example, I think a lot of languages, if we take a notion like body, they're like the onset and the nucleus are actually simultaneous. They get linearized, but they are simultaneous. So there are pieces of the phonology that seem to act like syntax.
Yeah, I think that's, I mean, I wouldn't dispute that. I mean, so maybe the way to think about it is that, there's linear relationships, and then there's these dominance relationships. And the idea is that, in phonology, you can make use of a linear relationship, and many times you have to make use of it. So for example, like in English, the word cat and the word act, they have sort of the same, speech sounds, but we know they're different words. And so we have to, in our mind, somewhere in our brain, that temporal order of those speech sounds is there. Because when we say cat and act or tack, these are all distinct words. And if we didn't have a representation that kept track of linear order, we wouldn't distinguish those words, but we do. So I'm not disagreeing with your point that there are some words or some representations maybe where linear order is not important. We might also think about, there's probably in the phonological literature, people have proposed that these, secondary articulations on some sounds are also just, there's no linear order there, that they get linearized in a certain way in the phonetic production. Fine. So no one's saying that that's not impossible, but we are saying that phonology can make use of linear order, and they do, in many cases they have to. And then I would say that the dominance effects that we might argue, that people have argued that we see in phonology, maybe they're there, but they're not actually meaningful, because ultimately you can break them back down to a basic linear type relationship. Whereas in syntax, you've got to have the dominance, or at least there are places where you need to have the dominance. Whether the linear order or not in syntax, I think that's probably a debate people are having.
I mean, maybe this is wrong thinking, because I'm not a phonologist, but without really needing ordering, can't you just invoke a notion like body and coda, and then you wouldn't need to worry about ordering between them? So then cat and act are very, very distinct without really ordering each element.
Yeah, I mean, it's a great question. And one of the things that I didn't talk about in today's slides, but that I'm very interested in, and I think it's been another advance actually. So I think maybe if I do this talk again, I'll try to put it in. But one of the things that we've been able to do with the logical representation, with the logic and what we call model theory. So model theory is a way of describing the structures that we're interested in, whether they are sequences, whether they're more articulated structures like you've described, where you have syllable structure that's associated, and you maybe have some kind of relationships among the syllable structure. We can compare distinct representations of the same things, and we can come up with a logical translation between them. And we can look at how complex that logical translation is. The idea being that if there's a very complex logical translation between two representations, then the representation is actually, meaningfully different. Because we always have this question, like, when do two representations, what do you get from a new representation? Like, what is it actually getting you? Or is it just a notationally equivalent to something else? Well, the power you need in translating between one representation and another in terms of its logic is a way of measuring how distinct two representations are, how much you're getting out of another one. And when my former student Cristina Estrella Garcia completed her dissertation, she looked at questions similar to the one that you're raising, where she looked at different representations of syllable structure, where in her case, they were, you've got a syllable node with an onset node and a coda node and a nucleus node. And then you've got, this representation where maybe you're just putting a boundary symbol between the syllables in the sequential order. And she showed that the translation you need, the logical translation you need to go between these, is actually what's called the quantifier-free logic. So it's actually a weaker logic. And so I would say that, one of the tools that we have in our toolkit now that I don't think we use so much in the 20th century was we can actually answer questions like the ones that you're providing by saying, okay, let's look at those representations. Let's see what kind of logical translation exists between them. And we can measure, and we can see exactly what that, what the benefit and what the cost is of the new representation. And that's exciting to me. That's what a lot of work we're doing is actually like that. There's some papers in phonology recently about that I'm happy to, they're not on that question, but on other structures in phonology. Yeah,
thank you.
Hi, Jeff. I'm sorry to say that I think I have to end this meeting, and that question I think has to be the last question, because there is another special talk in 3 minutes.
Everybody should go there. So thank you very much again, everybody, for your time. I've really enjoyed it.
Yeah, it was amazing. Thank you for doing this.
Thank you so much. And send me an email if you have any questions or anything. Happy to follow up on anything. Thank you so much.
Yeah, thank you, everyone.
Thank you, Jeff. See you soon.
Bye-bye. Yep, see you, Vinny.
Thank you.